Thank you very much. I'm Mr.Benard Ochieng, a teacher of chemistry from Agoro Sare High School. We want to continue with the applications of electrolysis. In our previous lesson, we did see some of the applications of electrolysis. One, the extraction of very reactive metals, for example, sodium, magnesium, aluminium. We also saw another one, purification of copper, and also electroplating. Today, we want to look at how to obtain sodium hydroxide in large scale and also chlorine in large scale using what is called a downcell. Now, in downcell is a kind of a setup that is made in such a way that if you look at this kind of a flow, kind of a chart, there is brine coming in here. This brine is concentrated sodium chloride, And then we have these positive electrodes. These positive electrodes are made up of carbon, particularly the graphite, and or sometimes you can use titanium. I've said it is graphite or titanium. The essence of using them is because they don't react with chlorine. That is the reason why we use carbon or graphite. So when you feed this mercury cell, we call it a mercury cell because there is a thin film of mercury which is our cathode, which acts as our cathode. There's a thin film of mercury which moves around. It moves this direction like that. So when this mercury cell is fed with brine, as I've said, is concentrated sodium chloride. This anode will attract the negatively charged ions. Remember, brine is made up of sodium chloride, and because it is concentrated, it is dissolved in water, and therefore there are some water molecules and also sodium chloride dissolved in it. So in this case here, we shall have chloride ions and also hydroxide ions, which are negatively charged in this particular solution. But because of relatively high concentration of chloride ions, hydroxide ions cannot be discharged in here. That's why you see chlorine coming out. This chlorine is coming out despite water being inside here. Reason being that this brine is concentrated sodium chloride, and there are more chloride ions in this particular solution. And because of its relatively high concentration, it is the one to be discharged. Chlorine. Now, and then, because now the chloride ions, they lose electrons here to form chlorine, sodium ions, the electrons that are lost are acquired by the moving film of mercury, which forms our cathode. Now, this moving film of mercury is moving around like this. There's a pump here to ensure that it moves around. Sodium ions from this end will dissolve in it to form what is called sodium amalgam. We are going to illustrate that one using equation. Now, sodium amalgam is just sodium dissolved in mercury. Remember, mercury is very poisonous. So once it has been dissolved here, the mercury flows with it, the amalgam flows. And in the lower part end of this mercury cell, there is water coming in. You see water coming in here. Once water has gotten in this particular part, this water will react with sodium metal from sodium amalgam. Now, we know that when sodium reacts with water, it forms sodium hydroxide and hydrogen gas. That is the reason why you are seeing hydrogen gas coming out. This caustic soda is just sodium hydroxide. The common name for sodium hydroxide is called caustic soda. Sodium hydroxide now comes out. Now, remember, the sodium amalgam which flows in this direction, this amalgam, as I've said, it is made up of sodium and sodium dissolved with mercury. So in the lower part up to somewhere here, what will be left in this particular mercury amalgam? There will be no more amalgam, but it will be mercury because sodium shall have reacted with water to form sodium hydroxide and also hydrogen. So the mercury that is left will be regenerated and will flow through the system once again. And that's how sodium hydroxide is obtained in large scale, and this hydrogen again is also obtained in large scale and now can be taken to where it's supposed to be used. For example, large scale manufacture of ammonia, large scale manufacture of hydrochloric acid, chlorine can as well be taken to where it is required large scale. For example, large scale manufacture of these detergents, we call them the bleaching agents. Also, in the case of purifying water, it also helps in the purification of water in water treatment plants. So the following are the explanations. As I've said, sodium hydroxide is being manufactured using, is being obtained from mercury, using mercury cell. The electrolyte is the brine, and the anode is made up of the carbon or titanium, and the cathode is made up of moving film of mercury. Now, when the electric current is passed through the sodium chloride, that is brine, the chloride ions are preferential discharge, the chloride ions, and as I've said, because of the relatively high concentration. So this is the equation for the reaction taking place at the anode. And we also have the sodium ions and hydrogen ions migrate to the cathode, moving film of mercury, but hydrogen ions are not discharged. If you are asked why is hydrogen ion not discharged, please, you mention because of overpotential or excess power required to discharge it, and that is why sodium ions are preferential discharge. So in this case here, sodium ions will pick electrons to form sodium, which will appear in liquid state and dissolve in hot mercury. So once the sodium ions has been formed, it dissolves in hot mercury to form what is called sodium amalgam. This is the formula of sodium amalgam. And then sodium amalgam is passed through a trough of cells that contains distilled water, as I've explained in the flowchart, to form sodium hydroxide and hydrogen gas. And then the mercury is regenerated and recycled. So in this case here, we are seeing indeed sodium amalgam reacts with water. This two is supposed to be subscript. Sodium amalgam plus water to form sodium hydroxide plus mercury plus hydrogen. So 2 moles of sodium amalgam requires 2 moles of water to form 2 moles of sodium hydroxide, 2 moles of mercury, and 1 mole of hydrogen gas. That is how we obtain sodium hydroxide in large scale and also chlorine in large scale. We are going to see the quantitative electrolysis, quantitative determination of electrolysis in our next lesson. Thank you very much, and I hope you have enjoyed. Keep listening. Thank you very much.